Okay, so maybe we can start today's lecture in the European Non-Associative Algebra Seminar. And it's a pleasure for me to introduce Duc-Khanh Nguyen, who is at the moment a postdoc at the State University of New York at Albany, and who did his thesis in France, in Lyon, with Kenji Iohara and Resser. And he is interested in representation theory, Schubert calculus, and algebraic combinatorics. And he will speak to us about the generalization of the Murnaghan-Nakayama rule for K-k-Schur functions and K-Schur functions. Please go ahead.
Okay, so thank you so much for the introduction and giving me an opportunity to give a talk in the seminar. So today I will talk about my recent work on generalization of the Murnaghan-Nakayama rule for K-k-Schur function and K-Schur function. So first I will explain about the motivation of our research. So let f to be a function in a variable x. We say that f is a symmetric function if it does not change when we apply any permutation sigma in the variable x. Now next lambda to be the graded ring of a symmetric function in variable x with coefficient in z. Next lambda power n to be the set of all symmetric function of degree n. Then there are well-known factors lambda n has a z basic given by the set of all Schur function S lambda, where lambda is a partition of n. For example, there are some classical symmetric function here. So the first one is an elementary symmetric polynomial. So it's given by the sum of all monomial x, I1 to xir, where the index I1 to ir are taken from the interval 1 to n, and they are strictly increased. And I denote this the elementary symmetric polynomial by er. So the second one is a complete homogeneous symmetric polynomial. So it's given by the same formula like elementary symmetric polynomial, but here the index are taken from the interval 1 to n, and they are greatly increased. And I denote the complete homogeneous symmetric polynomial by SR. The third one is a power sum symmetric polynomial. It's given by the sum of x1 power r to xn power r, and I denote the polynomial by PR. The next one is a Schur function associated to a partition lambda. So it defined by the determinant formula. Now in the theory of symmetric function, we consider some fundamental rules, namely net lambda to be a partition of n and r to be any integer in the interval 0 to n. So we consider the first fundamental rule named Pieri rule. It gives us the branching rule to the sum of Schur function of the power of the product of elementary symmetric polynomial with Schur function, or the product of homogeneous symmetric polynomial with Schur function. Now from the Pieri rule, we can obtain the branching rule to the sum of Schur function of the product of power sum symmetric polynomial with Schur function. So it named Murnaghan-Nakayama rule. And also from Pieri rule, we can obtain the Richardson rule. So it gives us the branching rule to the sum of Schur function of the product of two Schur function, S lambda times S mu. Now there are some connection between the theory of symmetric function with other domain. So the first one is a connection with representation theory. So for example, we consider the representation theory of generalized linear group, GLN. I suppose that lambda and mu here are partition, and in this case, we can associate a partition lambda and mu to irreducible module V lambda and V mu. So the central problem in the representation theory is understanding the branching rule of the tensor graph of two irreducible modules into the sum of irreducible modules. So we want to compute the coefficient C lambda mu nu appearing in the branching rule V lambda tensor V mu here. So to do that, we associate the character of V lambda with the Schur function S lambda, and the character of V mu is associated to the Schur function S mu. And now by the little Richardson rule for S lambda times S mu, we can compute the coefficient C lambda mu nu. Now to compute the character table of the symmetrical roof, we can do this by using the Murnaghan-Nakayama rule. Now similarly, in the cohomology theory of Grassmannian, we consider the cohomology ring of Grassmannian, and we know that the ring has a Z-basic parameterized by partition lambda, and we denote the Schur class associated to lambda by sigma lambda. Now, a central problem in the cohomology theory is try to understand the degeneration rules of the product of two Schur class S lambda times S mu to the sum of S nu with certain coefficient. So to compute the coefficient in this branching rule, we also associate sigma lambda to S mu to S lambda, and sigma mu to S mu. And now we apply the Littlewood Richardson rule for S lambda times S mu. We can compute the branching rule for the product of two Schur class L sigma lambda times sigma mu. So it have an application in the counting problem in algebraic geometry. So for example, if we consider four general line in the positive spec of dimension 3, and we want to know what is the number of line L mid on line L1 to L4 here. So to answer this problem, we transform the question into the question in the cohomology theory. Here we consider the Grassmannian of all subspec of dimension 2 in a complex spec of dimension 4. So I denote here by GR42. And we know that the cohomology ring of this Grassmannian has a Z-basic parameterized by partition lambda inside a square of psi 2. And the branching rules in this cohomology ring of this Grassmannian is given by the Littlewood Richardson rule for the symmetric function. And from this, we can compute sigma 1 both 4 times equal 2 times of sigma 1 square of psi 2, and with coefficient 2. And the coefficient appear in this degeneration rule is exactly the counting number for this geometric problem. Now, similarly, we study the quantum K theory of a flat variety, for example. So, namely, we replace the cohomology ring by quantum K cohomology or quantum K homology or K cohomology and K homology, and we replace the Grassmannian by a larger variety. And what we want to know is the Murnaghan-Nakayama rule in the quantum K theory, but in the symmetric function version. So more precisely, we study the alpha Grassmannian, I did not here by GR. And we know that in this case, the homology ring of alpha Grassmannian had a Z-basic parameterized by partition lambda, such that lambda 1 not greater than K. And in this case, I denote the Schur class associated to lambda by sigma lambda K. Now we want to compute the product of two Schur class sigma lambda k and sigma mu k to the sum of Schur class sigma nu k with some coefficient here, I don't know, by star. So to do this, I have to associate sigma lambda to a symmetric function. In this case, I denote here by s lambda k, and we call this one is the K-Schur function associated to lambda. Now, from the theory of symmetric function, if we can compute the literal Richardson rule for two K-Schur function, we know the branching rule for the product of two Schur class. Yeah. Now, similarly, when we replace the homology ring by K-homology ring, we know that in this case, the K-homology ring of alpha Riemannian also had a Z-basic parametric bipartition lambda, such that lambda 1 not greater than K. And in this case, I denote the K-Schur class associated to lambda by theta lambda K. Now, similar question. We want to know what is the branching rule for theta lambda K times theta mu K. To do this, I also have to associate K-Schur class theta lambda K to another symmetric function. In this case, we call K-k-Schur function associated to lambda, and we denote it by G lambda K. Now, if we can compute the product of two symmetric functions, G lambda K and J mu K, into the sum of J mu K with certain coefficient star here, we will know the branching rule for two K-Schur class theta lambda K and theta mu K. Now, before we go to the main result, I need to introduce some definition. So first, I suppose that lambda here partition. So that is a set sequence of non-negative integer lambda I, such that they are weakly decreasing. And for each partition, we can associate or understand it through a Young diagram. So the Young diagram associated to lambda is set of box, such that in the first row, we have a lambda 1 box, and in the second row, we have a lambda 2 box, and so on. And the box in the netmost side are in the same column. So for example, when I consider lambda here, even by 4, 2, 1, 1, so I can draw the Young diagram associated to lambda by this picture. So you see, in the first row, I put 4 boxes because lambda 1 equals 4, and in the second row, I put 2 boxes because lambda 2 equals 2, and so on. For the third and the last row, I put 1 box. Now, the conjugate partition of lambda, I denote here by lambda t. It can be obtained from the Young diagram of lambda by reading the Young diagram of lambda in column. So if you read the number of boxes in the first column of lambda, you obtain the first component of lambda t. And if you read the number of boxes in the second column of lambda, you obtain the second component of lambda t, and so on. So for example, here I also have lambda t, the conjugate partition of lambda, still equal 4 to 1, 1. But we change the way we read the Young diagram. So first I read the number of boxes. I read the first column of lambda, I get 4 boxes. And next I read the second column of lambda, I get 2 boxes, and so on. For the third and the last, I get 1 box. So that's why I get lambda t given by this one. Now I suppose that mu should be another partition, and it contains lambda. So I can define the skew Young diagram, a skew shape, skew partition, mu over lambda, given by this Young diagram. So namely, we'll remove the Young diagram of lambda from the Young diagram of mu. And we call this skew shape your ribbon if it does not contain any square of side 2, 2. So for example, when I choose mu here, here 4, 2, 2, 1, 1, 1. Then I can draw the Young diagram of me by this picture here. And now we know that contains the Young diagram of lambda. And by removing the Young diagram of lambda from the Young diagram of me, we obtain the skew shape me over lambda. Yeah. And in this case, you see that this skew shape is a rib bone, because you cannot find any square of side 2, 2 inside this skew shape. You see there only one box here, and two box here, and we cannot find any square of side 2, 2. And now when a skew shape is a rib bone, we can define the height of a skew shape or height of a rib bone. So it's given by the number of vertical domino in the skew shape. So go back to the example, you see. Inside this skew shape, one box here and two box here, you only can find only one vertical domino. So that is two box in the bottom of the skew shape here. I mark here. So that's why I can compute the height of this rib bone is 1, because we have only one domino vertical dominance. And now for a partition lambda, such that the first component lambda 1 is not greater than k, I can define 3 maps between lambda and some element inside the in the alpha symmetric group and another partition kappa lambda. So more precisely, I denote S k plus 1 delta to be the alpha symmetric group. So that is the group with generator S0 to Sk, where the index are taken from modulo Z to k plus 1 Z over k plus 1 Z. And it satisfies 3 relations. So the first one is the square of x element, x generator, E identity. And the next to second is a breadth relation. I denote here by A and B. And we denote the subgroup of the alpha symmetric group here with generator S1 to Sk by Sk plus 1. So that is the symmetric group. So to be simple, I just write the element Si1 to Sik by Si1 to Sir by Si1 to Ir. Now I start to define the map of phi, S, and P here. So I do not give you the general definition. You can find in my paper. But here you can understand the map through this example. So I consider the k equal 4. And I suppose that lambda equal 4 to 1, 1. Now I want to define the element W lambda inside the alpha symmetric group. So if given, you can understand the process like this. So first, because k equal 4, I write 0, 1, 2, 3, 4, and I repeat. So I get the first rows. And now for the second row, I shift the first row to the right 1 step. And I shift the second row to the right 1 step. I get the third row and so on. And now we start to fill the shape of lambda to the table. I have a crease here. So because lambda 1 equals 4, so I put 4 red circle in the first row and I start from 0. Next, lambda 2 equals 2, so I put 2 circles on the second row. Start from 4. And so on for lambda 3 and lambda 4, I put 1 row. Now 1 circle, 1 red circle. And now I read the table, I mean the tableau with a red circle here. I have a crease here. In this direction, I start from top to bottom I start from bottom to top, and in each row I read from right to left So you see, I start from the bottom here and I read the entry 2. So I get the first one, the first entry 2, the first index 2. And now I go to the third row, I read the entry 3. So I get the index 3 here. And now I go to the second row and I read from right to left. I get 0 and 4. So you see 0 and 4 here. And now I go to the first rows. I read the entry from right to left. I get 3, 2, 1, 0. So that's why I get 3, 2, 1, 0 here. And we get the element W lambda. And now the map from W lambda to I find the map from W lambda to kappa lambda. So I do the same where before to create the table. I write 0, 1, 2, 3, 4, and I repeat to get the first row, and then I first row one step to the right, I get the second row, and so on for the third and the fourth, and so on. And now I try to fill. I read the index here of W lambda. So I start from 0 here. So you see that when I read 0 on this tableau, we only can find one position, 0, so that we still have a partition. So that is the 0 here in the first row. And when I read 1, you see that there are only one position, 1, that is in the third row and right after 0. So that we have a partition. In this case, 0 and 1, the partition is 2. And now for 2 and 3, I also have only one position for 2 and 3. They are in the first rows, right after 0 and 1. So here. But now when you read the entry 4, you see there are 2 positions, 4 in the first row and 4 in the second row, right below 0. So see, you have a partition now is 5 and 1. So that's why I put 2 circles, for 4 in the first row and for 4 in the second row. And similarly for 0, I have a 2 positions. So 0 in the first row right after 4, and 0 in the second row right after 4. So that's why I put 2 circles for 0, first and second. And now for 3 and 2, I have only one position, such that it makes a partition when I put a circle. So I put 1 circle in the third row and 1 circle in the fourth row. And now I read the shape of the tableau. A press circle I have grid here. So you see, in the first rows, I have a 6 circle, red circle. So that's why I put the first component of kappa lambda to be 6. And in the second row, I have a 2 circle. So that's why I put 2 to be the second component of kappa lambda, and so on for the first and the last row. I have 1 circle. So I put 1, 1 for the last component of kappa lambda. So that is the map sigma S and P. Now I denote AK to be the associate algebra over Z with generator I0 to AK. Here the units are still taken from the modulo Z over K plus Z. And it satisfies the relation A and B. So A and B here are the break relation to define the alpha symmetrical group. But I replace S, the generator SI by generator AI. And so to be simple, I rewrite the element AI1 to AIR by AI1 to AR. And now let K to be a non-negative integer, net annoy của K, and A here proper subset of Z over K plus and Z, such that the cardinality of A equal R. So I can define two elements, dA and IA. So D here mean decrease, and I here mean increase. So dA given by this formula. So A of I1 to IR, where I1 to IR is a rearrangement of A, so that if I and I plus 1 belong to A, then the index I plus 1 or could be for index I. So for example, when K equal 4 and A is a subset of Z modulo phi Z, so we given by 0 to 4 here, I can find dA equal A of 0 to 0, 4, 2 and A 0 to 4. And now by reading the index of dA from right to left, I can automatically get the expression of IA. So that is given by A 240 and A 420. And now we can define the non-commutative homogeneous symmetry function as R by taking the sum of all elements dA, where A are taken from the subset of interval of the interval 0 to K of cardinality R. Similarly, we can define the non-commutative elementary symmetric function ER by the same formula for HR, but I replace the element dA here by IA. And from SR and ER, we can define Hook-Schur function by this formula. And I denote this one by S R minus I and 1 power I. And then I can define the power sum Schur function as power sum symmetric function PR through the Hook-Schur function. Yeah, by this formula. Now I suppose that sigma define an action of algebra AK on the group ring of alpha symmetric group. And then a function from a function per C from AK time alpha symmetric group to the set real number is said to be phi comparable, phi comparable. If it satisfies this relation. And now for a fixed phi and per C, we can define the set of a family of symmetric function here denoted by FWK, where the index W here belongs to the set of minimum coset representative of alpha symmetric group. So that is satisfied three conditions. So the first condition is the definition for F at the identity. Yeah. And the next two condition is the form of Pieri rule. So the first one is the Pieri rule for F for the homogeneous symmetric function. And the next one is the Pieri rule for elementary symmetric function. And now, by the bijection between partition lambda and element W lambda in the set of own, in the set of minimus set of own minimum coset representative in alpha symmetric group, we already defined before here. This one, lambda with W lambda. We can define the function F lambda K through F W lambda K. So for some, so There are some examples we consider here. So the first one is the action of AK on the group ring of a phi-symmetric group is given by the formula. So AI acts on W will be SIW if the length of SIW greater than the length of W. And it equal W is the length of SIW less than the length of W. And in this case, if I choose a C, defined by this formula, you can check that this function satisfies the free compatible relation here. And in this case, we know that the function FWK coincide with the K-k-Schur function GWK. Similarly, when we replace the action of the first example by the formula, so in the case of when the length of SIW less than the length of W, instead of setting the image by W, I put the image of action by 0, and we replace the function Phi here, upper C, sorry, by 1. So you can see that this function satisfies the compatible relation here. And in this case, the function FWK coincide with the K-Schur function SWK.
Excuse me.
Yeah.
I have one question. The capital K, what does it stand for?
You see K, because of okay, go back to this. You see this.
I see.
K here is that's defined by this condition lambda 1.
Yes, but the capital K.
Capital K.
The K-k-Schur function. The capital K.
K mean K theory.
Like in K theory. Okay.
Yeah. Because this one is a version for homology ring. And now when we put K homology, you understand. This one is for version for K homology, and this one for homology.
Okay.
Capital K here means K theory.
Thank you.
Okay. So now when we pick up a word in the algebra IK, I can define the support of the word by taking the index appearing in the let's say the index appearing in the expression of the word, and I set it by S, and then we can define the canonical cyclic interval of S by 2 steps. So the first you define the minimum element inside in the interval 0 to K, such that it does not belong to S, and I denote this one by A. And now the canonical cyclic interval of S EIS is given by the order. So you set I plus 1 less than I plus 2 and less than I plus 3 and so on, and then you go back to I minus 1. So for example here, if I choose U by the word 0, 4 to 4 in algebra A4. Now the support of U is a zero-own index appearing in the word. So you see only 0, 2, and 4. So that is the support, and I denote here by S. And now you see, if you embed S inside the interval 0 to 4, so you first write 0, 1, 2, 3, 4, and you see there are 2 index that does not belong to S, so they are 1 and 3. But here 1 is the minimum entry that does not belong to S is 1. So I set 1 here by A. And now the interval IS is given by 2 less than 3 less than 4, and then you go back to 0. So you have this one is a canonical cyclic interval of S. Now we call a word is K-connected if S is an interval of IS. So for example, in the previous example, you take S equal 2, 4, and 0. And you already know that IS is this one. 2 less than 3 less than 4 and less than 0. And now you see when you embed S inside the interval IS, you remove the entry 3. And now when you remove the entry 3, you see the interval is divided to 2 parts, and that's why you say that S here is not for connected, because you have 2 disconnected interval, 2 and 2 here and 4 less than 0. Okay. Now we say that U is a weak hook word if it have a reduced word of form decrease and then increase. And we say that the hook type of this word is V. The reason we choose the capital letter V, because the shape of V is also like decrease and then increase, or it has form decrease and then UI equal UI plus 1 for some index I and then increase. And in this case, we say that the hook type of the word is U. The reason we choose the capital U, because the shape of U also like decrease and equal and then increase. So for example, when I choose U equal 4, 0, 4, 2, 4. And now by this order here, you can draw the of the word U. So that is 0 decrease to 4 and 4 decrease to 2, and then from 2 we increase to 4. So the shape of U of the word U in this case is V. Note the number of accent of the hook form with respect to the canonical cyclic interval IS by ASCU. So in this, you see that in the example, the number of accent equal 1, because you only have a 1 increasing step 0 at 2 to 4. And now next CU is a set of consecutive pair A less than C such that A different from similar to 1. And there are no B in between A and C in the hook form of U. We define the index semi by the minimum index C among the pair A less than C in CU. And we know that the number of index semi only belong to the set 0, 1, and 2. So for example, in this case, when you look at this word, you see that there are only pair C with a gap between them 4 net and greater than 2 and 2 less than 4. And so we can see that same in this case is 4. And in this case, 4, you see 4, yeah. You look at this one. You see 4 appear in the left side and the right side of the word U. So I put 2 red dot here because 4 appear in the 2 sides of the hook type. Now, in general, we can classify a word U to 3 types. So a word U can be connected or disconnected. And in the case it is not, it is disconnected. There are two possibilities. The number of same mean equal 2, or number of same mean equal 1. So if the number of same mean equal 2, or the word is connected, we call the word is weak connected. And in the case, if the number of same mean equal 1, there are two possibilities. Same mean on the left of the hook tie, or same mean on the right side of the hook tie. So for the first case, I did not, I mean, I call them, I call the class not quick connected, and I put left because same mean on the left side of the hook form. And in the last case, I call them weak, not weak connected, and I put because same side of the hook form. So we encode the information of a word by some notation here. So for example, when I write big V and I WC and I put R above, mean WC here. Sorry. I mean R here, R above the capital V, means the number of letters. Because that this one is a weak length of the word. And V, the capital V, means the hook tie of the word. So the hook tie of the word is V. And I, the index I here, means the number of accent of the word U. And WC means weak connectors. So for example, you can check this word 0, 4, 2, 4 belong to the set W big V, one weak connected and 4. Similarly, we use notation U, I, WC and R, or U, I, WC, I put bar and I put never right. Depend on the size of same mean on the hook form. And you can check this one. You can check the example. I mean the not example, the two remaining two example here. Now I will state the main result. So to be simple, I first denote. I use some kind of notation here. I put F equal and I put a dot above and some S, mean F is a set, is the sum of all element U when U are taken from S. So the first lemma gives us a cancellation-free formula for power sum symmetric polynomial. So it's given by this formula. So the element inside, I mean the element that contribute to the power sum symmetric polynomial here are the hook, I mean weak hook word of type V or U. And it satisfies certain condition related to the number of words R and the number of accent I, and the hook type, I mean the connected type may be weak connected or not weak connected. And in the case not weak connected, we require the condition that the index same mean on the right must be on the left. Sorry, on the index same mean must be on the left side of the hook form. And now from this number, we will obtain the Murnaghan-Nakayama rule for the function f wk in more general setting. So it require the condition that the function uv only depend on the weakness of the words equal R in this case, and the image of the action U on element W, I denote here by W prime. and the element W itself. So because it only depends on these three variables, I can rewrite it as a function perceive delta in variable R, W prime and R and W. And then the Murnaghan-Nakayama rule for FWK is given by this formula. So you see, you just put the value of the function perceive delta outside, and inside bracket you just take the sum of with the sum over the cardinality of the sets that contribute to the formula of power sums above in the lemma here. You just count the number of elements inside the set, and you put some certain coefficient here with precise coefficient. And here I put W prime above the notation V, mean that is a subset of onward U, such that the action of U on W equal W prime. And the index W prime here run over all element inside the minimum length concept representative of alpha symmetric group. Now there's the first corollary we obtained from general Murnaghan-Nakayama rule. So if we consider the action of AK on the group ring of alpha symmetric group by this formula, you see, and you know, before that, in this case, FWK cosine with K-k-Schur function JWK. So I obtained the Murnaghan-Nakayama rule for K-k-Schur function. So the fourth formula here. And now because of the bisection between W prime and partition mu, such that mu, the first complement mu1 is not greater than K, I can translate the formula, the rule, the first one, the fourth formula, to the second formula, but in terms of partition. And when we translate the result in terms of partition, we can find more conditions. Here you see there are 5 conditions on the partition mu. So that we know that if mu satisfies the condition, then the coefficient here will be non-zero. So somehow it gives us a more precise formula than the first formula. And the condition here, it does, it's some condition or overmotion. And everything already defined before. Next, there are other corollary. When we consider AK on the group ring of alpha symmetric group defined by this action. And in this case, the function FWK cosine with K-Schur function. And in this case, you can easily see that the action of AI square on W equals 0. In this, if you suppose that AI acts on W equals 0, so nothing to prove. But now if you suppose that AI acts on W is non-zero, so it should be SIW by the definition here. And now when you apply one more time, you get SI times W. So you remove Ni square because Ni square equals identity. So then the name of SIW decrease 1. And so that's why you obtain 0 when you apply AI on W twice. So from this is the key point. From this key point, AI squared acts on W equals 0. You can simplify the Murnaghan-Nakayama rule for K-k-Schur function to obtain the Murnaghan-Nakayama rule for K-Schur function. So you see here, I use this formula for K-k-Schur function, and I obtain this formula for K-Schur. You can see some modification here. First, you remove all set of type U. There are no U here, because when you pick up a word of type U, then there are some index UI equal UI plus 1. And now you apply this identity AI square acts on W equals 0, then it gives you 0. So that's why you have to remove all word of type U. And now you focus on the whole word of type V. You see that even for the whole word of type V, we also can simplify the formula. So you see here the condition for word of type V should be connected. And in the on the formula for K-k-Schur function here, the word require condition. So it means that require stronger condition here connected. The reason is that when we pick up any word that is with connectors but not connectors, then by definition here it should belong to this guy. It should be disconnected and the numbers of semi equal 2. And so it means that there are two index semi on the left, right, and the right side of the word view. And then by the disconnected condition, we can we can obtain another word that give you the same value by removing the index C on the right to the left. And then you see there are two index semi appearing together, and it gives us image 0. Yeah, AI square as on W equals 0. So that's why you have to remove the condition with connected by, you have to replace the with connected condition by connected condition. And then you can obtain a simpler formula for K-Schur function in terms of partition. And the result here are already done by Schilling and Zabrocki and Bandlow in 2011. And we also find an effective algorithm to find the set of set which contribute to the decomposition. In each case, or K-k-Schur function and K-Schur function. And then in hand, we can compute the coefficient easily by hand. So for example, I will give you some application of the theorem and visualize the algorithm can able to compute the coefficient here. So I consider the k equal 4 and r equal 4. And now I suppose that I want to know the Murnaghan-Nakayama rule for K-k-Schur function with partition lambda equal 4 to 1, 1. And I suppose that the partition mu here equal 4 to 2 to 1 appear in the Murnaghan-Nakayama rule. So for example, mu here. And I want to compute the coefficient of J mu K in the Murnaghan-Nakayama rule. So the first step, I then need to find the partition kappa lambda associated to lambda. So you already know how to find kappa lambda by this bisection. This one. From lambda, we will know how to compute kappa lambda. Now similarly, we can find kappa mu from mu given by this one. And now we start the algorithm to find the coefficient. So the first because k equal 4, so I write 0, 1, 2, 3, 4 and repeat. I get the first row, and then I shift the first row to the right one step, I get the second row. And then I shift the second row one step to the right, I get the third row and so on. So I get a table of entry 0 to 4. And now I start to fill the shape of kappa lambda here to the table. So first I remove the shape of kappa lambda from the table. So we remove here. And now I keep the shape of kappa mu in the table. So I write here, I draw here. And then I obtain a skew shape, a skew thumbnail. So the first one, the first entry 1, the next entry 1, and 4, 3, and 1. So the skew tableau here contains 5 entries. And our algorithm on this skew tableau gives us a hook word, the set of hook words here. So you can find the algorithm in my paper, but here I will add mention directly the result. So it gives us 6 words. But and now you start to record the information of the word. So the first one is of type V and with one accent, and it is weak connected word, and so on. For other words. And now you see how to remove the 5th word here, because you look at the formula, the Murnaghan-Nakayama rule for K-k-Schur function. You see, there are no, for the word of type U, so that they are not weak connectors. We require the condition that same mean on the left of hook type. So this one, the next one. But you see, this word 1134, it have hook type U, and it is not weak connectors. And in this case, the same mean is on the right. So that's why we have to remove this word. And then you apply the formula of Murnaghan-Nakayama rule. We already know before. We obtain the result here, the coefficient of J 4 in the product P4 times J lambda 4 E minus 3. Okay, so now I will talk a bit about the future direction of research. So the Murnaghan-Nakayama rule for FWK, it not only covers the result for K-k-Schur function and or K-Schur function, but also cover a lot of other symmetric function. So you can see in my paper here, they cover the dual K-Schur function and or R5 stable organic polynomial and closed K-Schur function and closed K-k-Schur function and so on. So the first direction is give the detailed representation of the Murnaghan-Nakayama rule for all symmetric function I mentioned here. Now the second direction is translate the Murnaghan-Nakayama rule for FWK here to the Murnaghan-Nakayama rule in quantum K cohomology of flag variety or quantum cohomology of flag variety through Peterson isomorphism and K-Peterson isomorphism. So the Peterson isomorphism is an isomorphism between homology of alpha Grassmann and quantum K cohomology of flag variety. And K-Peterson isomorphism is an isomorphism between K homology of alpha Grassmann with quantum K cohomology of flag variety. So the isomorphism associate X Schur X function J lambda K and SK to a Schwarz class. And so the Murnaghan-Nakayama rule for K-k-Schur function and K-Schur function will be transformed to the Murnaghan-Nakayama rule in quantum K-homology of flexibility and quantum homology of flexibility. And that is another direction. So we find the version in quantum K-homology and quantum homology of flexibility. So that is all I want to talk today.
Thank you for your talk. So maybe you have some questions?
Yeah.
Yes, I had a question.
Yeah.
You showed us that the K-k-Schur functions and the K-Schur functions come up from different actions of AK on this group algebra of S tilde.
Yeah.
And so the last examples in your future work, do they also come from actions of AK on the group algebra? Or
You mean here?
yes.
Yeah, it also come from another action, but instead of acts on one partition, you see, for example.
Okay.
Yeah? Instead of acting on one partition.
Yes.
I mean, you can understand that W here partition. In fact, W here is an element in alpha symmetric group of minimum length in the coset representative. But you know that this is also associated to a partition by this one, by this map. Right? So somehow you can understand this action is the action of AI on a partition. You see? Okay. And well, and now we'll go back to the question. The other symmetric function, not K-k-Schur function or K-Schur function. Here we also define it through the action of AK on group, on the group ring of alpha symmetric group. But here instead of partition, it may be the sum of certain partition.
Okay.
We just replace the formula, but it's still defined through action of algebra AK on the grouping of alpha symmetric group.
Okay. I see that there is a question in the chat.
Yeah.
So there's a question, are there any generalizations related to braid groups?
Braid group? I think it covers, because you see AK here. AK here is I don't know. I still don't understand. What do you mean by you mean replace AK here by braid group?
Replace.
No, I mean, you see that
replace affine groups.
Yeah.
Is writing.
You mean replace? Yeah, I mean it have a generation for general but braid group, but here I only consider the the alpha symmetric group, the group of type alpha group of type A. But there already know, I mean, there are already have some Murnaghan-Nakayama rule for the Y group of type BCD.
Mm-hmm.
But in this case, I only consider the Y group of type A. There, in fact, they already have some paper work on type B and C and D. But when you try to generalize my result with the result with type BCD, there are a lot of modification. So for example, here, you cannot define the cyclic, this one, canonical cyclic interval anymore. Because, for example, when you work with type B or C or D, you do not have a linear order, but you have an order like a poset order. And there are a lot of modification, but you can generalize this one to any type, Lie type ABCD.
Okay, thank you very much.
Yeah, thank you.
Thank the speaker again. And we meet next week.
Okay, thank you.
Bye.
See you.
Thank you, bye. Danke, Friedrich.